In this example, we're going to look at how to use Stokes' theorem to first convert a surface integral of a curl flux into a line integral around the boundary, and then also look at how to relate that original surface integral to an integral over a totally different surface. In both cases, we'll see that we can take a very difficult problem and make it much easier. So here we've got this surface that we've denoted S1. We're using the index 1 because we'll be introducing a different surface later on. But this surface S1 describes the top half of the surface of the ellipsoid x over 2 squared plus y over 2 squared plus z squared equals 1. So I've sketched this in yellow, and I've drawn a normal vector to this surface to show you how it's oriented. It's important to keep in mind that this surface is open underneath, so in the xy plane there's no surface there. So for this surface, we'd like to evaluate the flux of the curl of f across this surface, where f is the same vector field that we encountered in the previous problem, and I did this just so that we wouldn't have to calculate the curl again. So on that note, let's remind ourselves that grad cross f here worked out to be equal to 0, 0, 1. Now this is a pretty simple curl, but even still, trying to integrate the dot product between this vector and a normal to the ellipsoidal surface is going to be very non-trivial. So we need to find another way to evaluate this flux integral. And the solution comes to us by using Stokes' theorem. So flipping Stokes' theorem around, we have that the integral over this surface S1 of the curl of f is equal to the integral over the closed curve C of f dot dr, where the closed curve C here is the boundary of the surface S1, oriented so that if I point my fingers around in the direction in which it's traversed, my thumb would point in the direction of the normal to the surface S1. So the boundary to S1 is this circle of radius 2 in the xy plane. And it's oriented this way. So let's call that C. And so we'll determine the value of this surface flux integral by instead evaluating this line integral around C. So to evaluate that line integral, I'm going to need to parameterize that curve C. So I can write that as r of t is equal to, it's just a circle in the xy plane of radius 2. It's got to go counterclockwise when viewed from above, so I am constrained a little bit in how I describe this, but my usual parameterization works here. 2 cosine of t, 2 sine of t, and 0 for the z component. This gives me r prime at t minus 2 sine of t, 2 cosine of t, and 0. And my vector field, when z is equal to 0, is just equal to x plus y, and x. And so plugging in my parameterizations for x and y, I get that f of r of t is equal to 2 cosine of t, 2 cos t plus 2 sine of t, and 2 cosine of t. Taking the dot product now between f and r prime gives me minus 4 cosine of t sine of t plus 4 cosine squared t plus 4 cosine t sine t. One of the z components is 0, so that just gives us a 0. I notice I get some nice cancellation happening here, and this just leaves me with 4 cos squared t. And so this, along with a dt, is what I would plug in here. Right, that is f of r of t dotted with r prime of t dt. So let's evaluate that line integral. It becomes the integral t running from 0 to 2 pi. Oh, I forgot to give that. T runs from 0 to 2 pi here. Of 4 cosine squared t dt. I'll use the identity that cosine squared is equal to 1 plus cosine 2t over 2, and then integrate that. And this will give me 4 times t over 2 plus 1/4 sine of 2t, evaluated at 0 and 2 pi. When I plug 0 and 2 pi into sine of 2t, I'll just get 0. And when I plug 2 pi into t over 2, I'll just get a factor of pi. So my final answer is 4 pi. So this is the value of the line integral around the boundary of S1. But this was still a fair chunk of work to evaluate. There's actually an even easier way to do this. And this is to relate my original surface integral to a surface integral over a much simpler surface. So notice that my boundary curve C for the surface S1 is also the boundary curve for the disk of radius 2 that sits in the xy plane here. So let's call this S2. And it's basically the disk x squared plus y squared is equal to 4 in the xy plane. So I started off with this Stokes theorem relation, relating my surface integral to the boundary curve. Let's bring this down here. And I solved this problem originally by relating that surface integral to the line integral here of f around the curve C. But since S1 and S2 both have C as a boundary, it should be true that that line integral is equal to the surface integral over S2 as well. In other words, I have over here a surface integral over this half ellipsoid, and my first equality relates this to a line integral around the boundary. But then my second equality relates this to a surface integral again around this disk of radius 2. And what's nice about doing this is that this disk of radius 2 has a really simple normal. The normal to this is just the z hat vector, which is equal to 0, 0, 1. And I've already got grad cross f is equal to 0, 0, 1. So for S2, I'll find that grad cross f dotted with ds2 is equal to 0, 0, 1 for grad cross f, dotted with my normal for that surface, 0, 0, 1, and then my regular surface area element. So that just works out to ds. In other words, I'm just integrating 1 over this disk of radius 2. And if I'm just integrating over this disk of radius 2, I'm just going to get the area of that disk. It's got radius 2, it's a circular disk, so it just has area pi, r squared, and r is 2, so that's equal to 4 pi. So just to make this perfectly clear, right, this is the same integral here. I've just replaced grad cross f dot the normal vector with 1, because that's what it works out to be. And so effectively, I related my original flux integral over S1 to a flux integral over S2. And this second flux integral was really easy to work out. And comparing to what we got for the line integral, which was also a lot easier than working with the original surface, I got my answer of 4 pi again, which is always a good sign. Alright, so this is another trick that you can do using Stokes theorem. And that's all I wanted to show you in this example. Thanks.